Hello everyone. So welcome back to another video of Marin Maths. And on today's video, I want to bring a very special experiment. Since today is going to be a snowy day, so there's going to be a snowstorm all day until tomorrow. I'm going to take the advantage and an opportunity to go outside and experiment with snow. So previously in one of my videos, or a couple of them, I had mentioned that I was studying the behavior of snowballs rolling down snowy inclines. And so, since it's going to snow a lot, right, about between 12 to 18 inches, I think it's going to be a good, a good setup for the experiment. So, since I already found two papers that have mentioned how the behavior, the kinetics of the snowball will turn out to be. I looked at two papers, one from the University of Columbia, from the National University, and one from Princeton University. I believe both of them have very good arguments, and I want to see if their arguments are experimentally reproducible. So, for example, McDonald wrote this paper last year on March 12, 2019, and I mean, think about it. It was still like, I think it was still spring, right? So if you think about it, last year it didn't snow a lot, so it was difficult, I think, to prove this experimentally by the people from this, so the people that worked on this paper. So in this paper, I guess the key points that they mention here is that the acceleration, for example, behaves as this function. So they say that the acceleration of the snowball, right, that's rolling down an inclined plane with uniform distribution of snow is going to be the gravity divided by 5 sine of the angle of the incline minus 7b, which b in this case will be the depth of the snow. So in this case today will be between 12 to 18 inches. The depth b is going to be dependent, right? So it's going to be the independent variable here for the acceleration, multiplied by some constant of integration c, divided by 3 times pi r0 squared plus bx to 10 thirds. So the r0 means the initial radius of the snowball. And you know that as the snowball starts to roll down the incline hill, it's going to increase its radius for one of its sides, right? So it's not going to be a uniform distribution, of course. That's a very physical assumption to say that the snowball's shape is always going to be spherical. So instead, we're going to rely on the assumption that it's not spherical and that indeed it becomes a log. It tends to become a log at infinity, at t equals infinity, because at that time it's just going to keep on, rolling down with respect to a flat plane, which just will flatten the snowball even more, making it a log. So maybe we should experiment with snowballs and also logs of snow. So, and the function you see is proportional to 1 over r squared to the 10 thirds plus bx to the 10 thirds. So what this means is that as x approaches infinity, x is the distance traveled, the acceleration will approach g over 5 sine alpha. I want to prove this experimentally. I want to see if I can make a very long incline and see if the acceleration will indeed level out and will be constant afterwards. I'm not sure how to do that, right? So, I mean, if the acceleration is constant, right, if you think about it, then we can integrate this twice, take a double integral to find the position, and then find the distance traveled. So it could be, it's going to have a lot of percent error, but if it's not too bad, then I guess Mr. Kirk is going to be right to find the acceleration. I still didn't take a look at the entire paper because it's not trivial, right? It takes me a while to read it. It's a lot of mathematics involved. It's a very mathematical problem. So he splits the problems into several parts, right? Just like anybody who knows calculus will do, split the problem into smaller parts, then add everything together. So for example, on part 3, he talks about the single turn of a rolling log. And then he moves on to essentially analyze the behavior and the dynamics of the snowball or the log, right? He does torque analysis, energy analysis, all that kind of stuff. Okay, so it's a very, very informative paper. It was just published last year, so it's relatively new. And there's pretty good links here that I have to still take a look at. So I'm going to see if this is experimentally reproducible, and the mathematics are non-trivial. So wish for luck, and let's take a look at this video to just give us a hint of how snowballs will behave on snowy
Welcome back to Top 5s. Today, we're doing the top 5 snowballs.
Okay, so you can see this one are relatively big, very large snowballs. Alright, so now that's important, right? The snowball collapsed. The snowball just collapsed after some time. So there's so many other factors involved in this problem, like what's going to be the total structure inside of the snowball. What if the structure is not uniform, right? That means that the distribution is not uniform. Because if it collapsed, there were some points that were not strong enough to hold the entire spherical solid, right, of snow intact. So this is important to consider, right, for a more realistic setting. Sometimes it will just collapse after it increases its speed.
All right, snowball.
Now over here, they're trying to bring it down. Of course, I'm going to make relatively small snowballs. I don't want to make something like this. Just something that's manageable and that can be controlled.
Come on.
Okay, so you see, once it hit the flat surface, it just collapsed. Right? The force was too much for it to, stay still. Let's see.
This is a hill.
Let's see this one.
And this.
Okay, so pretty big one. There it goes. So, okay, notice how the thickness increases, right? So notice how the thickness only along its radius, right, along its surface, right, point. So where the surface touches the ground is the only one that's going to be increasing its thickness. So that's why the radius is not constant all throughout. It's changing, and so the volume is changing as well. And then it collapses. Okay, remember seeing some of these that did not collapse?
Sophie said no.
Okay, there it goes.
Uh-oh.
This one I think is going to go farther. And it still behaves, right? So notice that initially it was kind of very spherical, right? And then after some time it flattens out and becomes a log. So the analysis of the log is actually very reasonable and has a good point, right? Because as the sphere tends to roll and roll and roll, as t approaches infinity, it's going to become a log, right? No matter what, because it's just rotating on a flat surface. So there's no other choice of form, right? There's no other geometrical solid that will take place other than a log. So that's
Zachary,
a
you
good,
can't get that
good
ball
choice.
back.
Oh, okay, look at this. So many people there. Alright. Yeah, so notice the thickness increasing only on one side, and of course its course, its path is changing, but that's because the incline is not uniform. And also the imperfection is normal.
Here's a few more clips that didn't make the list.
Okay. Everyone. Alright, so yeah, but you get the idea.
Yeah.
Okay, so wow, that's really heavy.
Watch out!
So yeah, that's the idea for today.
Go, go, go!
Since it's going to snow so much, right? Why not take advantage of it to study the mechanics in these conditions? Oh, look at this one. So the depth, right, is probably a lot more, which means that the thickness will increase by a lot more, and so will the acceleration decrease. Notice that the speed is not as much, right? It's not speeding up as much. It's actually speeding. It's going to slow down eventually, and maybe this has some fundamental, you know, truth over here on this equation that A is equal to g over 5 sine alpha minus 7b, the depth of the snow, divided by 3 times pi initial radius squared plus depth of the snow times distance traveled to the 10 thirds. So eventually, as b approaches, if b is very large, of course, right? If the depth is a lot, then of course acceleration will remain constant at t equals as the distance traveled is greater and greater, then the acceleration will level out. Its asymptotical behavior will be at g half fifths sine alpha. So yeah, that's the idea for today. And so for today's experiment, I have some things ready. I have a balance ready, right, to measure the weight of the snowball initially, or the snow, or the the log. So I also have some stuff, to try to make it as spherical as possible, right? Something like this, like an ice cream scoop. So this one might actually help, get a spherical shape. I should have bought, the snowball maker, but I didn't have time for it. I didn't think the snowstorm was going to come so soon. But there's that, and there's also, like duct tape. So I have duct tape, and I probably have something spherical somewhere. So I'm going to test those to be the control group. So I want to see how the acceleration, how the distance travel and the speed behaves compared to the snowball. So yeah, that's going to be it. And it starts snowing at about 2 p.m. until tomorrow, Thursday, in the morning. So I will probably go out somewhere in the afternoon when the accumulation is good enough for the experiment. All right, guys. So I'll keep you updated and see you soon. Enjoy your snow day.